Hi, this video is about the true power of energy explanations in physics. Let's start with a simple example of a little wind-up car. If you've ever seen one of these before, you wind up the little spring and you let it go and the car zooms off, right? There's also, I used to have one that you like pull back and then let go. Same kind of deal. Let's say you do 10 joules of work winding up the toy car, which stores 10 joules of potential energy in the car's springs. And then you let it go. What happens? It starts to move forward, right? But as it moves forward, it doesn't actually translate all of that potential energy into kinetic. There's a little bit that turns into thermal. As the gears turn and the axles, rub up against the surfaces of the car's body, thermal energy gets produced. Heat is generated. And so a little bit of that potential energy becomes thermal energy, while the rest becomes kinetic. Even though the car started out with 10 joules of potential energy, only 8 joules of kinetic energy gets generated, so it's not completely efficient. But what I wanted to show you this for is if you look at the number before and the two numbers after, you still have a total of 10. And this is important because while mechanical energy is not always conserved for different systems or machines or toys, the total energy always is conserved. And another way of saying this is energy never just appears out of nowhere, it never disappears, but it changes from one form to another. This is known as the law of conservation of energy in physics, and it's an extremely powerful concept. I've talked before about how when we try to explain things in physics using forces, it's like using a hammer. Hammers are really powerful, they get the job done really efficiently, but they're pretty limited in their versatility. They really just do one thing, they hammer. I guess you could pull up nails with it too, but oh man, I'm about to lose my, okay. And then we talked about how momentum is like a screwdriver. It's very useful in certain situations. It has a very practical application in certain kinds of scenarios, and you need a screwdriver for it. But one tool that's even more powerful than those is energy. And energy, I said, is kind of like a drill, where a hammer will get the job done, a screwdriver will help you do certain things, but a drill has a lot of power. It can go into different situations and really make things a lot easier and helps us to put things together a lot better. So that's what I think of when I think of the powerful impact of energy. And let's look at another example of that. How energy helps explain where we get, all of our energy from is mostly from the sun. Let's say that you have the sun shining down on this landscape here. Let's pick out 100 joules of electromagnetic energy from the sun, light energy coming down from the sun. What happens to all that energy when it reaches Earth? Well, it can take a variety of different paths, and I've tried to illustrate this here kind of crudely, but you can see the energy comes in and some of it bounces off clouds and bounces off the ground and gets reflected back into space. About 20% of it actually does. So 20 joules go back into space. Other bits of the sun's energy get absorbed by clouds and by the air, and that stores thermal energy in the air. Some of it gets absorbed by the water or the ground that's on the earth, and so you lose some of it into thermal energy in the ground or in the oceans. But some of it's captured by trees and grass and plants, and so it gets turned into chemical potential energy. But more things can happen too. This is just a few examples, but energy can get, basically split up and broken up into different pathways as it reaches the earth. And that's, part of what makes energy so useful is it goes in so many different ways and we can use it to explain so many different things. As an example, here are some things that energy helps explain. As you can tell, I've worked very hard on these drawings, so you can appreciate them here. A great example of energy is eating something. I'm trying to draw a watermelon. It doesn't really look like that, but a watermelon being eaten is chemical potential energy that you take into your body, and then your body uses that to turn it into mechanical energy. You're moving around, you're doing things, your heart is pumping, your blood is flowing. You need mechanical energy to live. Every living thing does, and we get that from the chemical potential energy in our food, which originally came from the sun. Photosynthesis turned it into, stored energy in plants. plants get eaten by us or by animals, and we eat the animals, and so we get our energy from the sun, ultimately. Another example is a stove cooking some kind of pot, right? We have electricity that often stoves are plugged into. You can also have gas, but the stove is electrical, so you plug it in, electrical energy becomes thermal energy on the stove. Another example, electromagnetic energy hits a leaf, and the leaf captures that energy and transmits it, transforms it into chemical potential energy in the molecules held within the leaf. Another example, I use this one a lot because it's easy to experience yourself. If you slide against the ground, you get carpet burn or floor burn, or sliding on the dirt here. Mechanical energy that you were moving turns into thermal energy. You feel it, especially if you've ever had carpet burn. You feel that thermal energy from all that mechanical energy that you did have. When you slide, your mechanical energy goes away, but it doesn't disappear. It turns into thermal energy. And then one more example, say you're singing into a microphone, right? As your voice, carries energy with it, it hits the microphone, turns it into an electrical signal, electrical energy, which can also be transported into another speaker. And so it comes out as acoustical energy again. So these are just a few examples of how energy helps to explain what's going on in our world. So that's all I've got for you in this video. Remember, this day could be your last, so live on purpose.